Okay, I want to go over how to find critical values. To make this concrete, let's start with this example. Let's say we wanted to find out the heights between which we have 95% of people. Okay, so we're going to have this distribution of heights, and again, height is a continuous random variable because it results from a measurement. And it's going to be, all of our various measurements are going to, fall somewhere along this range. And remember that what we're looking at here are z-scores. So z-scores are the difference between the actual value and the mean divided by the standard deviation. So this gives you the number of standard deviations above or below the mean that the observation is. So for example, if the average height might be something like 5'10", then the z-score of 5'10", because it's exactly equal to the mean, would be 0. So it's 0 standard deviations away. Okay, so something lower than this would be a certain number of standard deviations below it, and something above this would be a certain number of standard deviations above it. So what we're looking for when we're looking for critical values is a z-score. Okay, so let's say we've got this range here, and this is 1 standard deviation above, this is 2 standard deviations above, this is 1 standard deviation below, and this is 2 standard deviations below. Okay, so let's say we want to find out, okay, I want to include 95% of the entire population. I want to find out what are the heights that would contain 95% of people. Okay, so it might be something like, if I had to take a guess, something like between maybe 4'9" and 6'9". That would contain maybe even more than 95%. But I know that this range would contain a large number of people. Whereas if I were to say, okay, 5'9" up to 6'1", this would not contain 95% of people. This might only contain 80% of people. Okay, so these values here are expressed in raw scores, but they are critical values on a certain height distribution. Okay, so we can see that 95% of people would be between these two values, and 80% of people would be between these two values. So what we're looking for when we're trying to find a critical value is these numbers along the range here, but we want to find them in terms of z-scores. Okay, so number of standard deviations above or below. So let's say we're going to do this height question, and we've converted all of our raw measurements to z-scores, and we have this distribution here. I want to find, and I'm just going to draw a line, to chop this off at a couple of places here, just guessing, and say, okay, I want to find the area in here that includes 95% of all of the people. Okay, 95%. So find the values along here, this one and this one, such that 95% of the the observations, or 95% of the area under here is between those two values. Okay, so these two here, so we're going to have a left critical value and a right critical value. Okay, so we're finding two-tail values here. Two-tail. That means there's going to be one on the left and one on the right. Okay, so how do we go about finding these? Okay, so what we have here is a normal distribution, and we can use the normal distribution when we have n greater than or equal to 30. Okay, so if I have taken at least 30 people, then I can find the critical values this way. So, okay, so the critical values typically on a normal distribution then are going to be abbreviated as Z, okay? And there's going to be a subscript here to indicate how much area I'm really looking for. Okay, so let's look at this one up here and say, okay, well, if 95% of people fall in here, that means how much area do we have out here in these two tails? Okay, so if there's 95% in there, that would mean we've got 5% left over. Okay, so this is a symmetrical distribution, so we would have to cut this in half, right? So half would be over here, half would be over here. So we would have 2.5% of people in each of these tails. So this would be 2.5%, and this would be 2.5%. Okay. So the subscript on this Z then is going to be something called alpha over 2. Now, when we get into hypothesis testing, we're going to talk more about what alpha means. But basically, if we are looking for a 95% confidence, okay, so that's what we're doing when we're saying, okay, find 95% of people. We're finding a confidence interval, a 95% confidence interval that will, it'll contain 95% of people, okay? So that's a 95% confidence interval. And if your confidence level is 95%, this leftover 5% is just designated as alpha. Okay, and so this subscript is alpha over 2 because as a two-tailed probability, we have to put half in each tail. Okay, so we're looking for Z of alpha over 2. Okay, so this is what we're finding right here. Okay, so let's go ahead and find that. So this is going to be a standard normal. Okay, we've turned it into a standard normal by expressing everything in z-scores. So standard normal, mean of 0, standard deviation of 1. Okay, so how do we find this? Okay, we have a function in Excel that we can use. Okay, so it's a normal distribution, and we're going to use the INV. So an inverse function is one that's going to take a probability and give back a z-score, or in our case, this will be a critical value. So norm inv, and this is going to take 3 parameters, and the first of them is that the first of these is going to be that z of alpha over 2. Okay, so this is going to be this probability right here. So in this case, so we have to find 2 values, right? We have to find one on the left and one on the right. So remember that when we're using these cumulative probabilities, what we do is we count up the area from negative infinity up to a certain spot. So if we're finding this left one, so to find the one on the left, we're going to go up to this probability. So we can do 0.025, and then the mean of the distribution is 0, and the standard deviation is 1. Okay, so let's go ahead and find what that left critical value is. Okay, I'm going to come over here to Excel. Let's zoom in a little bit here. We can see better. Okay, so norm inv. Okay, so now see it prompts me with that probability. So for the left one, we're going to use 0.025, and we're going to use the standard normal parameters. Okay, and that tells us that left critical value is negative 1.95, but we'll round up to 1.96. Okay, so this is going to be equal to negative 1.96 on the left. Okay, so that's that one right there. So because we want to find 95% in here and leave 2.5% to the left and 2.5% to the right, we also need a right critical value. So the one on the right then is going to be, accumulating all the way from negative infinity up to this probability, okay? So it's going to include this 95%, and it's also going to include this 2.5% here, okay? So we're going to just go from negative infinity all the way up to this point, which will include this 95% and this 2.5%. So when we put it into Excel, we need to do norm inv 0.975 and then the same parameters. Okay, so let's go ahead and do that. Okay, so norm inv 0.975, mean 0, standard deviation of 1, and that gives us 1.96. Okay, so come here and put this in 1.96. Okay, so notice, critically that these two are the same, and that stands to reason because this is a symmetrical distribution. So in truth, once we know the left one, all we have to do is reverse the sign, and we have the right one. Okay, so this is what we do for a normal distribution, again, when we have n greater than or equal to 30. Okay, now if our sample size is going to fall something under that, then we have to do something a little bit different. And we can't use the normal distribution anymore because the normal distribution makes the assumption that you have at least 30. So there's another distribution that we can use, and this one was invented by kind of an interesting guy who used to work for the Guinness Brewery. It wasn't possible for him to get sample sizes that were sufficient to do certain quality tests. So he wanted to figure out, well, how can I find these critical values? How can I construct confidence intervals based on smaller samples? So how can I adjust the normal distribution according to how small my sample is? Okay, and incidentally, the reason it's called student's t is t was the name of the actual statistic, and student was it was kind of the secret name that he used because he wasn't supposed to be publishing as an employee of Guinness. They didn't want their competitors knowing that he had these secret weapons, so he just used the pseudonym student. So okay, it's the t distribution, and student is just kind of retained as kind of a historical interesting fact. Okay, so the idea is that because we have fewer samples, we need to change the distribution so that it's going to be wider. Okay, and how wide it is going to depend on exactly how far we are from 30. Okay, so let's take a look. So this is so finding critical values on the t distribution. So let's say we've got we're doing our same example where we're looking at heights, and this was our normal distribution. Okay, so this is the one that we would use if we had n greater than or equal to 30. Okay, so we found out that we would have 95% of the area here would be between negative 1.96 and positive 1.96. Those were the critical values we found. Okay, but this t distribution says, okay, well, based on how few samples I have, I'm going to change this so that I still want to include like 95%. Well, how far out do I have to go before I actually include 95%? So let's say we had, in the red here, we had, let's say we were only able to get 15 samples. Okay, so now notice that if we only have 15, we can't be as confident that we're going to have 95% in here. So this distribution is going to look more like this, where it's going to come out like this. We're going to have more that are further out. Okay. So now you can see that 95% of the area under this one is now going to be like, let's say, from here to here. Okay, and these, by the way, these tails keep going theoretically. Okay, so and if we have even fewer, let's say in another case, in the blue here, we only had 8. Okay, so now we can't be as confident that, you know, we're gonna capture 95% of people within, you know, a certain range. So we need to widen that range. So now we're looking at a distribution that's, you know, going to have even fatter tails here. So in order to catch 95%, we're going to have to go all the way out to here, you know, all the way to here. Let me bring this tail out here. Okay, so now we want to know, okay, well, given that we only have 15 samples, now what are the critical values that will contain 95%? Okay. Well, as you can guess, Excel also has an inverse distribution to use this. So let's go ahead and do the case of the red one first. So just like with the norm inv, we use the t inv, and the probabilities are going to be the same. So just like we put, you know, if we wanted 95% between the critical values, you know, this is going to leave 2.5% in this left tail over here. So we're still going to use 0.025. Okay, but now we have to put in some kind of parameter that tells Excel how many samples we actually have. And this is going to be approximated by something called the degrees of freedom. And we're going to set that equal to n minus 1. Now don't worry exactly what they mean by degrees of freedom. We're not going to go too much into depth with that. But note that degrees of freedom lets us put in how many samples we have, but we're actually going to be putting in n minus 1. So over here, so our degrees of freedom for this case, if we have 15 samples, will be 14. And if our degrees of freedom, abbreviated DF, is going to be equal to 7 over here. Okay, and so just like when we had Z, when we were doing a normal and we said, okay, well, this is going to be Z of alpha over 2, that was enough to tell the normal distribution, but for the T distribution, we actually abbreviate it. We have T, and we're still doing the alpha over 2, but now we also have to put in our number of degrees of freedom. Okay, so using this function over here, we're going to use T in 0.025, and then whatever our degrees of freedom are. So in the case of the red, this will be 14. So that'll be the left tail for that. So let's go ahead and find that. So going to Excel. Okay, so we're going to use t.in probabilities 0.025, and now the degrees of freedom, which was 14. Okay, so now negative 2.14. Okay, so negative 2.14. And I'm not going to bother calculating it because you know it's symmetrical, so that would mean the right tail is going to be 2.14, or the right critical value. Okay, so now let's do the blue one where we only had 8, so our degrees of freedom were 7. So come here to Excel again, and I'm going to just write down that this was 0.025 with degrees of freedom equal to 14. And so now we're doing 0.025 with degrees of freedom equal to 7. So it's going to be equal to t.in 0.025, degrees of freedom 7. Okay, and so negative 2.36. Negative 2.36, and so this is positive 2.36. Okay, so these then are the critical values. So notice that if we're going to make a confidence interval, that is, going back to our heights example, if we're going to make a 95% confidence interval where we say, okay, we can say with 95% certainty that the heights are between, this value and this value. If we have n greater than or equal to 30, that's going to be equal to, whatever our average height was, plus minus, okay, and it's going to be this critical value, so 1.96 times the standard error of the mean, okay, but if we only had 8 samples, we're going to have to do that mean plus minus 2.36 times the standard error of the mean. Okay, so you can see what happened here. Because we had fewer samples, in order for us to be 95% confident that this interval contained the true mean population population parameter of height, you see that we had to go out further. Okay, and so these critical values actually encapsulate how far out we have to go in order to obtain that level of confidence. Okay. All right, so that is for critical values for two-tail on the normal and the t-distribution. So again, we use norm.inv, and for a two-tail, we have to leave, for 95% confidence level, we have to leave 2.5% in each tail. So you're going to be using norm.inv or t.inv of 0.025 for that left, and 0.975 for that right. Okay? All right, so I hope that helps.